0.0104, lambda doesn't change, so that's why delta lambda equal to 0. And then x1 nu, you have x1 volt, and if you add delta x, that is this one, and lambda nu is the same as before, 0.05. So now, again you apply corrector because the error is a little bit higher, 0.02. So if you want 0.001 or something like that, you can put how much error you tolerate, because it should be, theoretically it should be 0, right? But in general you don't go to 0 there. So again with x1 nu and delta lambda 1 nu, so you get one more. You started here, you get another one corrector. So you update the Jacobian with this new x value, and lambda doesn't change. And then solve for delta x. Delta x is this. Delta lambda is 0. Actually, delta, you can also put limit on delta x. Delta x is almost close to 0. And so your x1 is, so then you have converged solution. So your x1 at this point is 2.823, lambda 1 is same as 0.5. So that is one predictor and the correct. So if you continue like that, so predictor corrector. One thing you ought to be careful here is, or understand here is, for example, near the critical point. So again, your predictor corrector, and if you iterate on the, for example, if you cross beyond this critical point lambda, then you have to iterate on the x value. So in this case, x value, to get back to 2.25 this solution. So this can be, you may ask, like, no, how do I know it is crossed, right? So one way to know that is one is obviously you may not get a solution there that indicates that you exceeded that value. The other one is on the bottom part of the curve, the derivative becomes negative. So the top part derivative is positive, or d lambda is positive, and the bottom part d lambda is negative. So from that you can decide, okay, now I have to switch the parameters so that I don't exceed that value. So even before that, maybe even before you come around this point, maybe you can iterate on the x value. Then you do x value, then you can you fix x value, because you already know what x values are here, right? Then you can get some x value and then iterate on that. One more thing, why the Jacobian may not become singular here is how do you choose the parameter? For example, if I at this critical point, if I choose lambda, if I choose lambda as my continuation parameter, remember at critical point this is 0, right? And 0 times 0, and this becomes singular. But if I choose x, and this is not singular, even it is 0, this is not singular. So that's the main point. Like, you know, I have a advantage of choosing the parameter such that I can avoid that singularity. So that's why you don't get into these singular problems. So that's the advantage of the continuation. And another advantage is I can continue on the bottom part of the curve, because I can get bottom part of the curve also. Whereas most of the power flow programs, if you see, they only do the upper part. That's okay, because most of the time you use only upper part, right? You don't need the bottom part. But as I mentioned before, in one of the examples you tried, some of the bottom parts may be also stable, or you can operate there. It is non-linear load. So in that case, you need a bottom part also. You don't need to stop there. You can get the bottom part. And in some of the cases, actually, people are trying to get unstable equilibrium point for Townsend stability studies. So in this way, like you can get both stable and unstable equilibrium points if you trace the entire PV curve. So you get some idea of unstable equilibrium points. Okay, so that's the basic continuation method. I will come back again when you talk about how you do in the actual power flow. This is a simple example I gave you. The one thing is, now we talk about lambda, right? What the lambda means in the power flow. So you know how to increase the P, right? You can think about P as the parameter. The real power is the parameter. But as I mentioned before, in this formulation, when we say lambda, that should be independent parameter, or independent variable that should not depend on x. So if I take the P, real power, we know if it is a non-constant power load, the real power depends on the voltage, that is x, right? So I cannot use P as the parameter. So then we have to say, how can I define the lambda? That we will talk about later. Okay, so this is the basic continuation method. And one of my colleagues, Dobson, his name is Doc. Remember in the first class, I talked about power faculty we have. Ian Dobson, he also worked initially on voltage stability. So the 3-bus system I told you, I showed you. This is his PhD, one of the PhD problems he solved when he was at Cornell. Actually, then he moved to University of Wisconsin as a professor, and then we asked him to come back to Iowa State. So he moved to Iowa State University. So he's at Iowa State University. So he proposed this methodology in the sense that now in the continuation power flow, you get the up to critical point, right? And this is one load direction. When we say PV curve, always this is one path, and I can increase load in different directions. Because power factor, right? One power factor, you get this one. Another power factor, you get another PV curve, and so on. So now if I know the boundary, critical boundary that I talked about, so we plotted that boundary. What he thought is basically, assuming I know that boundary, right? When I say what the boundary means, for each P and Q value here, you have singularity. Remember, any direction I can go, I can hit that. So you started with this, some initial real power and reactive power, and I can increase that in certain direction, right? That means certain P by Q ratio, and increase, when I am increasing the P, you are also increasing the Q at the same ratio. Now, depending on how you move, you will get different critical points. And then he has an idea that, okay, what is the shortest distance I can go? That means I have, right now I am operating here. What is the worst possible way I can change my load? And then I can hit the critical point or the boundary. So that means what load increase you have to avoid, basically. That's the thing, right? If I increase the load here, you have a lot of P you can increase. right? But if I am going in this direction, your P increase is very, very limited, right? So then he said, like, what is the worst case to increase the load, and then you have to avoid that. So you found, given an initial operating condition, what is the shortest distance from the S0 to the boundary? And the boundary, that's another interesting. The boundary, even though we have a nice curve like that, but it's not that nice, because any non-linearity, I think that gives trouble. So one of the conditions here is the boundary can be nasty. Oh. So he showed this is nice boundary, right? Maybe sometimes you can have a boundary like this, right? Then how can you say which one is the closest one? Then it becomes difficult. But within the range, assuming it is convex, like this, that boundary, what he said is, if I calculate the normal vector for the boundary, and if the load increase is in the same direction as the normal vector, and that's the worst case. The worst case load increase. That means basically what you have to do is, for him you need one boundary point. So that means you can use the continuation method, right? You can go along some direction and hit A, that is on the boundary. Once I have the boundary, I can calculate the normal vector there. So that normal vector is not parallel to the load increase. That means that load increase is not the shortest one. So then you take that one as the initial condition and proceed. So basically you iterate on that, where this N0 becomes your load increase there. Then you will stop. Okay, so first you need one boundary point, calculate the normal vector, and check that normal vector is same as your load increase direction. If it is not, take another one close to the normal vector, and then increase again and iterate. When both are similar, then you stop. I think that's the basic idea. So what is the procedure you have to have? Again, solve the power flow. Delta V lambda is equal to 0 at a given operating point, S0, P0, Q0. Select load increase direction, M0. This is load increase direction. Normal vector is, I don't know what, I have to be careful. I'm using the same symbol, but load increase direction is not same as the normal vector. So be careful. So select load increase direction N0. Search the system along N0 until Gx becomes singular. We already did that. And then let Si is S0 plus lambda M0, and let M0 star is the normal vector at A, right? So you have to calculate N0 star, that is the normal vector at A. M0 is the load direction, N0 star is the normal vector. I think that's the distinction. So Si, obviously when you increase this becomes SA, critical point. So at the critical point, find N0 star. Basically, how do you find N0 star? That find the left eigenvector W at A, and N0 star is showed that N0 normal vector is nothing but W, that left eigenvector you can calculate at A, that times GS. GS is nothing but the dou G by P and dou G by dou Q. In this case, PQ is the boundary, because in the PQ space is calculating the boundary. So this is the boundary, Jacobian at the boundary. with respect to the P and Q. And then select new load increase direction with N1 as N0 star. So now you are saying, okay, now this is the normal vector at this point, and repeat above steps until Nk star and Nk star are very close, and kth iteration. I don't know why. I said this, it cannot be star actually. It can be Nk. Yeah. Yeah, Nk minus 1, or you can say, yeah, maybe you can say Nk minus 1. Nk minus 1. Very close. That means basically you are iterating on that so that finally when you reach that, they are very close. Because remember, the N0, N1, N0, when you calculate, it may not be N0 star, right? Then you are imitating, equating N0 star to N1, and then increase it in N1 direction or N0 star direction, and so on. So that we have to do because this N0, even though you calculate a normal vector, but this is not, it depends on where you calculated that normal vector on the boundary, right? So that's why they are equal, only then you can say that's the shortest distance. So that's the basic thing. Again, now Skundur's book, if you go back on pages 107 to 112, he used this example to demonstrate. I think you also use the same example to demonstrate the continuation power flow also. So again, I started with 2 bus example. 2 bus just way to explain things. So again, generator 1 at an angle 0. You use minus alpha as the angle between these two, and reactance is 0.25, and P plus JQ is the load, and Gxs is equal to 0. S means in this case the parameters, that is P and Q. The parameters are in the P and Q is the boundary you are looking for, P and Q space. So that's why S corresponds to P and Q. So if you do that, basically these are the real power equation, reactive power equation, right? So it's like PV, P equal to V1 V2 by X sin delta, right? And again V square by X, EV by X cosine delta, right? The expressions you have, and same expression you are repeating basically here in P and Q. So you have these 2 equations that correspond to the power flow, or this function G, and your X is V and alpha, the voltage here and the current. And remember, now we have to calculate the Gx, as we did, because that for the boundary point I need the Jacobian. This is the derivative of the two functions. And the Gs, as I mentioned before, this is the dP d. So you are differentiating these two with respect to P and Q. So dou P by dou of this with respect to P, dou of this with respect to Q, again dou of this with respect to P, dou of this with respect to Q. Right? So that is this. Obviously you get minus 1 because here if I differentiate, it doesn't contain P, it's minus 1, Q is not there, Q differentiation is 0, and it doesn't contain P, so this is 0, first term, second term is minus 1. So minus 1, 0, 0, minus 1. We know that we can calculate it directly. Gx, determinant of Gx is singular, that means if we multiply these two, that is 16b minus 32b square cosine alpha, that is the determinant of the Jacobian, and I have to equate that one to 0. Right? So on the singular surface, determinant of Gx equal to 0, so that is equal to 0, and I can eliminate cosine alpha from this, that is 1 by 2v, and from that I can calculate sin alpha in terms of v, and if I substitute that here, and I can get the boundary surface. That means these are the alphas are the critical points. So if I substitute this alpha here, the P and Q are in the critical value, right? So P square plus 4Q minus 4, that's the one. Remember, that's the boundary is talking about. That's the PQ boundary. So that is the boundary. P square plus 4Q minus 4 equal to 0. And then you start with the original 0.8, 0.4, that's the initial powers, and at this power the voltage is 0.8554, and you go in this direction first, and calculate the normal vector, that's 1.843, 0.15, that may correspond to P and Q. So that's the new thing you take direction and you iterate N1, basically you get it should be parallel to this. This one should be parallel to this, even though I didn't draw the approximate. Then you get another N2 and iterate until N6, I think 6 iterations here. So now this is equal to N6. So in the same direction. So finally you end up with 0.9758, 0.7610. So this is the shortest distance, and you can see what is the p value, 0.8 to 0.97, right? So almost assuming it's 10, 0.1, so around 2.2, and here it is 1.8, almost 1. So here the margin is 1, and here margin is 0.2. So that means if I somehow increase the load like this, you are reaching the boundary quickly, then you are. So this gives you some ideas which loads gives problem, which load increase direction gives the problem, and of course, unfortunately, this is not in our control. You cannot ask increase the load in this direction, right? So that never happens because the customer is independent. But at least you know by history how the customers are increasing their loads, and based on this, okay, this load combination we have to watch for, because these loads are giving trouble. Because from the load increase, you already have history of that. From that you can say, okay, these directions, this is possible, some people are increasing in this way, and then that can create problems. So this gives some indication of that. Okay, any doubts? Okay, now coming back to the continuation power flow. Now we did for the single variable example. Now in the real power flow, how you implement that, right? So we know the PLI, the load power at a bus I, and reactive power at bus I, and I'm putting lambda because I'm changing the lambda. So you can represent that as a PLI 0 plus lambda times KLI, right? So what it means is both you are increasing the P and Q such that the power factor is constant because you are using same KLI, and this KLI gives one direction, that's why it's one direction. So if I fix KLI, that means I'm fixing the direction, and of course I'm also fixing the power factor in some way. So lambda equal to 0 corresponds to original load, and with some fixed ratio I'm increasing K, so that the PLI 0 is increasing and the PLI 0 is increasing. And one more thing, not only I have to worry about the load increase direction and also generation sharing, because when I increase the load, generator has to supply that load, right? Now how to supply that? So this one is tricky because you cannot again dictate. If it is a centrally controlled system, I can actually say this is the direction you can increase, but in the market base, so it depends on the economic dispatch. So that means I have to know for a given load increase, somebody does the economic dispatch, and for that load increase, which generators are participating, and from that I can calculate KGIs. So for that load increase, which generators are participating to supply that load? So that determines KGIs. So the main thing is somehow you have to come up with these constants. That depends on your practical system, like how you want to increase the load. For example, in the Mid-American system in Iowa, like when we do that, they know how they give the specific way to increase the load. From that we can calculate at that bus what is the projection of the load they want to increase. Okay, so then once you have that, the G, this is the equations of real and reactive powers. That's function of theta now, V and lambda also, right? Lambda, of course, lambda is independent parameter. Remember here, lambda is independent of P and Q. So that's why I call lambda is a connected load. So connected load means this PLI 0 depends on, of course in this case we are assuming constant power, but otherwise it becomes PLI 0 V by VI some K or some beta. PLI 0 V by VI some beta. Right? So yeah, if I can write PLI 0 for a nonlinear load as PLI 0 V by V reference times beta, then it is 1 plus lambda KLI. By doing so, I am avoiding the voltage dependent load increase, because now I change the lambda basically. So when I say increase the lambda, so I am increasing this much connector load of this type, right? This much connector load of this type, and this again depends on the beta, right? V by ratio. So the net value depends on beta and whatever the voltage you have at that point. So now I am not violating the mathematical requirement that lambda should be independent parameter, right? Then in this case I cannot increase P, but in this case lambda is approximately proportional to the P. Okay, so that's the one thing you have to remember. And then the predictor is same as before, G theta, GV, right? Original Jacobian, dou G by dou theta, dou G by dou V, or actually dou P by dou theta, dou P by dou V, dou Q by dou theta, dou Q by dou V. So that constitutes this. And then you are increasing, as I mentioned, one row, one column. This is G lambda, right? I am differentiating all the powers with respect to lambda, P and Q, right? G contains P and Q, and this is a vector, right? At kth unit vector, and this is the tangent vector, and this is plus or minus 1. Can you tell me why we use it plus or minus 1? Very good, very good. So because minus 1, when you wanted to trace lower part, you have to decrease the lambda, whereas the upper part you increase the lambda, right? So that's the plus or minus 1 is that. So your sorry, this is predictor. So this is predicted values of theta, voltage and lambda, that is original values plus sigma as I mentioned, step length and the tangent vector. Now what is the tangent vector here? D theta, dg and d lambda, right? So that is the tangent vector and that is the predicted solution. So initial guess here becomes this, right? And if you calculate the g value, it's obviously non-zero, right? And you fix lambda in this case and iterate along this. So gx star xk star minus eta equal to 0, k elements of x. So x contains all the three. So you can actually, technically you can choose any parameter you want, or parameter in the sense any variable you want to fix. Most of the time you fix that you already know. In this case lambda you are more convenient. So xk star minus eta equal to 0. So this is the theta star. Theta star is correspond to this one, and you substitute this, and first see this is 0 or not. It's not 0, then you basically now solve this. Solve means I have to calculate the Jacobian on that. Right? So that's Jacobian. Oh, I didn't show that. So you know that Jacobian gx. The same thing. One more thing. This Jacobian is same as this Jacobian. Jacobian doesn't change, right? That's why AT. So you can have one Jacobian. Only problem is this is one term calculation, right? So the Jacobian structure doesn't change, but the values change because they are the different values now. So sometimes what we did is we used the predictor value. Sorry, we didn't change the Jacobian and iterated the same Jacobian. Sometimes it converges depending on how flat the curve is. The curve is very flat, Jacobian doesn't change that much, right? Because you are calculating the Jacobian here. So if the curve is very, very flat, because you are calculating the Jacobian at the same point, so the Jacobian doesn't change. But if the curve is very curved, and then you get errors. So it depends on how close you are, or how far you are going on the predictor side to correct it back. Okay, so that's the basic thing, and we applied for large systems. We compared conventional power flow. It stopped somewhere here, and this is for base case without any contingency. So you can see not much difference between this point and this point, right? But if you look at the contingency, it stopped here, so around 1300, but actually the maximum power is 1800, so about 500 megawatts difference. So that's a huge amount of, because this is imports, remember? Imports and exports, that's business. So what we are saying is, if I use the conventional power flow, you said you cannot export more than 1300 megawatts. And we are saying that with correct one, you can export 1800. Of course, you don't do 1800, you have to maintain some margin. And also remember, this is, you don't decide by one contingency, as I mentioned before. This is one contingency, right? They have to do n minus 1 contingency. You do n minus 1 power flow or n minus 1 power PV curves and take the minimum of that. That is your transfer. So that's why the market people very much opposed to these restrictions, because we are if they want to avoid that, they can transfer a lot of power, right? But those contingencies, even n minus 1 contingencies may not happen, but they have to follow that. So that restricts the range of power they can transfer. And that's the reason also the utilities generally operate in conservative side, even major outages occurs, system still survives because they already backed away from the major critical points, so the system can survive. And again, one more thing we did is, even though I am showing here the paper, I provided some papers there, but this we call EQTP. This is we call equilibrium tracing program. So that is see, the power systems are represented by x dot equal to fx y lambda, right? And 0 equal to gx y lambda. When we considered slack bus, is it physically possible you can identify slack bus in the system? What is the meaning of the slack bus? In real life, there is no slack bus staying somewhere, and somehow it's look at the system and say which I ought to supply the losses, right? No, because for the problem we have is to solve the problem, because losses you don't know, right? Because in the power flow, generation should be equal to load, right? So I know the load, 100 megawatts or 1000 megawatts, but I have to commit not only 1000 megawatts of the generation plus whatever loss in the system, and I can get the loss only after solving the power flow, the network, right? Beforehand I don't know. So if I don't know the loss, how can you distribute how do you decide the generation? That's why they said, okay, put one generator as the unknown one, take all the losses there, and that's the way they solve the power flow. But actually there is one power flow, generally they don't talk about it, we call governor power flow. In the governor power flow, actually represent the governor, because the governor is the one that is balancing load and generation to maintain the frequency, right? Governor responds according to the load. It's not like slack bus responding to the load, right? The governor responds, governor acts by measuring the frequency, and if there is frequency deviation, then generator responds, oh okay, there is imbalance between the load and generation, and then they have to supply that unbalance. So in the governor power flow, actually in the steady state, they actually represent the governor function in the power flow. And also they are first order, the simple governor power, and also they represent the voltage regulator in some way. That's why I don't need even assume PV bus, right? So in that case, like I will get a true solution for the equilibrium. Then I don't need to depend on the power flow. But power flow, we do that because you do all these contingency analysis, right? For the moment, you don't worry about which one is taking and which generator is taking the losses and so on. To get a convergent solution, you assume some generators are slack bus and do the contingency analysis and make sure the system is secure or not. Once I know that, then I don't need to worry about it. You don't use the power flow to distribute the generation to the generator. The governor's job is that making sure that load is balanced with respect to generation. Okay, so in that case, the true equilibrium is x dot equal to 0 also, right? I have to solve these two simultaneously. Then I will get the 2x0 y0 lambda 0 if I solve that. So in the EQTP, we call equilibrium tracing program. So we represented governor and the voltage regulator functions and use the continuation method to good solution. So obviously it is better, little bit better than the with CPR. So you can see the it is 10 to the power of 5, even though it looks like 2.9 to 2.94, it looks the error is not that much because it's 10 to the power of 5. So that error is there with the CP flow versus EQTP. Actually, EQTP is more restricting than CP flow. So that's another one. And from the computational point of view, actually, this is which represented it's a large system, about 34 generators and 6,000 or around 7,000 buses. But if you calculate the one PV curve, not around 193 seconds and 148 seconds, it's not that much difference. So to that. Okay, that's the. So this is summarization. Conventional power flow for the calculate steady state for a given operating condition. Continuous power flow traces a series of power flow solutions for a given scenario. You can also trace the bottom of the PV curve, and the equilibrium tracing program is an extension of CPF. DAE instead of pure power flow equation is used to represent the power system. It has the capability of detecting both voltage and oscillatory instabilities. Because now I am using the two equilibrium, right? Now I can get ABCD matrices. For the system matrix A system, obviously you need ABD inverse C to get the stability or eigenvalue calculation. But as I mentioned before, one paper published in 80s or 90s that they used ABCD to extract the eigenvalues. So in that sense, if you have equilibrium tracing program, that can help the problem. Okay, so now look at some sensitivity analysis. One of the advantages of the continuation power flow is the tangent vector, right? This is tangent vector d theta, dv, and d lambda is basically, if you look at the tangent to the equilibrium point, so it gives some form of sensitivity, right? Sensitivity of the solutions by using the tangent vector. So what we did is, if I take any function you want, h x lambda, that is the like loss, for example, loss in the system, or generated reactive powers, and so on. So I wanted to know that function. If I want to know how that is changing with respect to lambda, right? Because if I am changing the lambda, that is the parameter. So if I assuming h corresponds to loss function, how the losses are changing with lambda? Because you already have these derivatives as a part of the solution, so I can actually calculate for a given load increase, whether losses are increasing or decreasing based on this sensitivity function. So what are the function? Hx lambda is whatever the function you are defining, you need the sensitivity. So if I want the derivative of that, from the mathematics we know for a x lambda, dh by d lambda is dou h by dou x first, and dx by d lambda and dou h by dou lambda. D lambda by d lambda equal to 1, right? So dx by d lambda is that. So you have dou h by dou x. If I know some explicit form of this function, I can calculate the derivative of with respect to x. Anyway, we are going the Jacobians. You are already doing that. And dx by d lambda. So dx and d lambda you are already calculating from the tangent vector, right? Dx, d lambda correspond to tangent vector. And dou h by dou lambda, again, if I know explicit function, and I can calculate the derivative, partial derivative of this function with respect to lambda. Yes, that's the idea. Now, bus sensitivity, for example, it's already there. So if it is voltage Vi, you know if I apply this, you get dy by d lambda, right? So dy by d lambda means how the voltage Vi is changing with respect to lambda. That gives locally, you get some information. And similarly, dy by d lambda is theta I. Yeah, you can get these are the derivatives. So that's not a big deal. For the branch sensitivities, that means H in the line ij plus j q loss ij, and actually you can calculate this loss in terms of the theta and v. Even for simple case, we showed that so h is a function of voltage, angle, and the network parameters, right? So you can calculate h explicitly with respect to voltage and current, because you know V I Vj, and you know how to calculate current, right? Vi minus Vj by, right? So you know that, and from that you can calculate loss. So you can derive the loss expression in terms of all these parameters. So then you can calculate dh by d lambda. So dp by d loss by d lambda, and you can also calculate dq loss by d lambda. And also generated sensitivity. X lambda I can define as QGI, and QGI you have a function, right? When you solve the power flow, you have expression for QG, right? So the QLI EI as QLI 0 1 plus lambda KLI. This is the load you are increasing. The expression you have, and the dh by d lambda is, now I can, this is the expression for this QGI. So dh by d lambda, then you have dou qt by dou xj, right? And dxi by d lambda, and kl, because if I differentiate that kli qli 0, and this is the differentiation of it. And these two already know. Only thing is I need to know the differentiation of this. Generally you are doing that already. You have that. So from that I can know reactive powers are changing with respect to lambda. That gives some idea of the sensitivities. So the tangent vector also you can use some form of sensitivity analysis. And then finally the margin sensitivity. How much time I have? Pardon? Up to 1 o'clock. So the margin sensitivity. It is first derived by Dr. Dobson again. If you look at his paper, and we derived in different way. But if you look at the DAE form, x dot is fxy p and lambda, right? This is the one I already showed you. There is a derivation. I didn't go through that for the lack of, to save you some time, but we can derive at the critical point lambda c. This is the total Jacobian, fx, fy, gx, gy, and this is the left eigenvector calculated at the critical point. So at the critical point, if I calculate the left eigenvector of this matrix, and if I multiply by left eigenvector of this matrix, that is equal to 0, and then you can derive the lambda c, right? So how that is changing? Now I want to see lambda c, that is the critical lambda, right? I wanted to see how that is changing with respect to parameter. P is not a power, it's not real power, it is any parameter you want to do. For example, if I wanted to do, because I am using a DAE, so if I wanted to say sometimes V reference, I think it's in Europe they do that. They control the reference voltage of generators. Remember in the even 2-bus example, we asked, like, effect of E, right? That E also depends on your reference voltage. So if I change that, you see you can get the different margin, right? E. So in Europe, actually they change the set points to control that voltage. So the P can be, you can also look at the how the set point change can increase, how much it increase the margin, so that you can, from that set point, you can say, oh, if I change by delta p, how much margin increase I can get. So if I, instead of putting 1 per unit, if I put 1.01, how much increase I get? Is it worth it to do that? So that's the idea here. So the partial derivative of the actual critical lambda stands with respect to any parameter. So this is the left eigenvector. We already saw VF transpose, VG transpose. This is left eigenvector, again left eigenvector. And the numerator is Fp Gp. That means the derivative of F with respect to the parameter, derivative of G with respect to parameter. And F lambda G lambda is the derivative of F with respect to lambda, G with respect to lambda. So getting this is easy, right? And this one, left eigenvector. So one more thing, remember the tangent vector? At the critical point, that becomes right eigenvector. You can check that, yeah. So at the critical point, that becomes right eigenvector. So if I want left eigenvector, generally if it is symmetric matrix, left eigenvector is right eigenvector, right? If it is symmetric. In power system, if you assume symmetric in some sense, generally off diagonal elements or similar. So if you assume that, then you can get this left eigenvector from the tangent vector also, because that becomes the eigenvector at the critical point. So that means getting this is relatively easy, and these derivatives anyway we can get the derivatives because f function, g function you already know. And the advantage of this is now I am considering the dynamic part also, dynamic side parts also. In the power flow, that's why the importance of the DAE or total equilibrium, because now I can consider the generator side parts also, and the dynamic side parts also, the gains, if we have SVC parameters and so on. So advantage of F, that way I can also include, whereas I have to only worry about only change on the G parameters, that's power flow parameter. And so relatively you can easily get that. So once I get this, for a given change in delta P, what is the delta lambda C? Delta lambda C is basically this partial derivative times delta P. So if I change this much, if I know this, the lambda will change this much. So PL critical nu is PL critical volt lambda delta lambda C times Kp. Remember Kp is the coefficient we are using. So this much power, it can be positive or negative depending on the which parameter you are changing. So it also indicates don't touch that parameter if you want to increase the margin, because if you get lambda, this becomes negative, for example. That means that parameter is not good to change to increase the margin. So from the sign of this, I can either increase the load, the critical load, or decrease the load depending on which parameters I change. So in my book, actually, we tried all the parameters. If you go back and look at margin sensitivity, we calculated for I think 2 or 3 bus system, and see which parameters are basically affecting the margin. So indirectly you can also know for voltage stability margin improvement, at least locally, which parameters you can change to increase the margin. And when I talked in the morning with respect to this PV curve, this is the assuming lambda c. So if I change the parameter delta p, then I get the, so basically you can think about that's a tangent, approximately a tangent. So this boundary is flat boundary, then you can change the large, the parameter variation can be, you can have bigger parameter variation. But if the parameter, this is very curved, the boundary like very curved again. So for example, this is the boundary and we are operating here. If I calculate the tangent to that, again, so if you estimate this is the margin, but actually you get into error, right? So that's why you have to be careful about the margin sensitivity. And if you look at my textbook there, some of the parameters are very linear. That means you can change large values, and some parameters you have to change very small values. If I apply this methodology, you may get errors. So you have to be careful how to do that. But again, computational wise, you do need the left eigenvector. That's another computationally intensive. If you are using just for margin sensitivity, first you need a critical point, and this critical point should be very, very close. It's not like you cannot approximate it, because the left eigenvector is valid only very close to the critical point. So some of the distinctions are there. Yeah, one more thing. I think yeah, the load I talked about. This is another important one. The PLI lambda, remember we said PLI 0 plus lambda KLI PLI 0, and I just now I'm separating, right? Previously I combined them and brought PLI 0 in the front, but if I don't combine them separately, it looks like this. So if I talk about L lambda, that is entire load that includes both P and Q. So you have L0 and lambda times K, and the K basically includes KLI, PLI 0 and so on, right? So KLI, PLI 0, that's the KPI I mentioned, and KQI. So KPI and KQI, and then K is I can define as a vector. One corresponds to the real powers, one corresponds to reactive powers. And if I want to know PL critical nu lambda c plus delta lambda c, so the PL critical volt before parameter variation and delta lambda t times KT. So when I talk about the KT, so that's the KT we are talking about here. So because when I say critical load, that is a vector. It's not one number, like each load level, what you get. So that delta P typically change in margin. So PLC lambda, and you have to see this is the change in the margin because of the change in the whatever parameter you are changing. So delta P L critical is delta lambda C and KP, and this is I1 I equal to 1 to n KPI. So so lambda C to lambda C dash, this is the lambda. So if I want this much change in lambda, how much parameter variation I have to, so that you will get this point without retracing any curve. So only I need this on some derivatives, so I can estimate this point. I think that's okay. Now quickly following this, we also tried after we went further and see whether I can trace this boundary, as I mentioned in the morning. sorry, morning means in the previous session. Margin sensitivity, as I mentioned before, it's like a tangent, right? So it's local sensitivity information it gives, margin, right? Now we want a complete path. How can I follow that path? So, so we defined, this is the margin boundary. So you have one point. So you want so this is one curve, right? And this is another critical point. This is another critical point. So you have these critical points. Somehow I wanted to so different loading scenarios according to base point control variation. So you get different critical points. So what we want to do is, if I join all these, this is the real margin boundary. Now I can take a tangent to that, and again you do predictor corrector on the margin boundary itself, because margin boundary already I can get, because I am putting the condition of the singularity. So this becomes your PV curve, so supposed to be. But this PV curve is margin, actual margin, not the any combination. So this is the margin actually. So we know for any, I have to calculate the tangent. So you get tangent predictor corrector, and actually I can trace that margin for the P, again parameter. It can be parameter, or if I consider that one as actually load, because previously it is limited to this, right? And you got to this by some control, right? Remember in the PV curves, you got that one by putting capacitors. So the capacitor is a control, right? With capacitor control, you got this the boundary, right? So if I use that capacitor is a continuous variable, B, susceptance is a continuous variable, I can take that one as a parameter and actually extend this to further increase. But the only problem is, similar to this, it can also curve back. So you get a n minus 2 singularity in the boundary curve. So then the method I cannot use single parameterization. So I have to use two parameterization. So that becomes very complicated. So we stop whenever it reaches the curved in the boundary itself, and it's too much, because even you observed in the capacitor, if you put too much capacitance, you already have higher voltages. So physically it is meaningless anyway. So you stop with physically meaningful solution. You don't go all the way to non-reasonable physical solution. I think that's right. And again, we published this paper, and if you need further detail from the research point of view, you don't get this in that the test. You don't worry about that. You don't get in the test this one. And again, security margin tracing. We also implemented this for oscillator stability, damping ratio, and same thing we implemented for all the three. So the idea here is basically it's like an investigating tool, that saying that this is, because this is computationally very intensive, right? So this is offline tool, and that can give you some of the boundaries you have, what is possible, what is not possible if you want to increase the margin. So it gives some ideas of where to change and what to change, some qualitative information you can get. Yeah, this is the basic approach of the margin tracing. So equilibrium condition that has to satisfy, augmented by margin boundary condition. That is basically singularity condition I talked about. The result in set of nonlinear equation of the form like this: Fg and C. This is some form of the singularity or margin boundary condition. So you have to solve this. Previously, direct method solves only one point, but here I already starting from that. So already I have this point. I have to go to the next point. That I already know, right? In the continuation power flow, if I have one point, even continuation power flow also, it has to start somewhere. You have to say one power flow solution you have to have. It cannot magically come up with a power flow solution. So you have to find a power flow solution and then proceed. Again, here also in the boundary, if you want to follow the boundary, you start with a boundary point. So once I have the boundary point, then it becomes easier because now I am only tracing the boundary. So that for me this is more informative rather than calculating directly the boundary. I can use continuation method, that's more realistic to do that. But the boundary tracing, I think existing programs cannot do that. So in that sense, yes, it is computationally costly, but you can systematically do this. So what we did is basically yeah, this is the already talked about this. Fast algorithm. This is then IEEE general publication proceedings, not IEEE transactions. We call proceedings of IEEE. That is another journal that special issues they publish. So if you check, I think everybody has IEEE Explore, right? Here, all the universities they have. So you can easily get this publication. And then I already talked about this. I think I will stop here. I will stop because I am going to the further details. I think they will saturate it. I don't want to push them with completely new things, and then yeah, I will stop here. Okay, so in the afternoon